Zoom on the keystrokes. Exploiting video calls for keystroke inference attack. I am Mod Sabra, and this work was done with a collaboration with Dr. Anindya Maiti and Dr. Murtaza Jaziwana. With the rapid innovation technology, faster internet speeds, and the higher demand for long-distance communication, video calls became a norm. Today, we can see video calls in work meetings, doctor appointments, classes, job interviews, or even personal communication between friends and families. Couple of examples of software that exist in the market for video calls are the web apps, Skype, Zoom, and Microsoft Teams. As the name implies, video calls contains two data streams, a video and an audio. During video calls, users often multitask. Sometimes they side chat with someone else, browse the internet, play games, process emails, type, or read articles. Now, while some of these activities might not be sensitive in nature, such as reading a newspaper, others can be very private and confidential, such as logging into your bank account. So now the question becomes, if a user types while in a video call, can an adversary infer what a user types during a video call, potentially obtaining the confidential information such as login credentials? The answer is yes. While a user is typing, an audio could be sent to the adversary. The adversary then uses the framework in Don't Skype and Type, which appeared in Agent CCS 2017, to predict the keys pressed based on the sounds of the key presses. Now, if a background noise appears, then the prediction could be inaccurate because the background noise, depending on its intensity and what type of background noise, could affect the model. Likewise, if the microphone was muted, then the adversary would not have access to the audio data. Without the audio data, he cannot apply the framework, which means he cannot predict what the person typing. We propose a new adversary model, a one that relies on the video data rather than the audio. When a user is typing, he usually have his webcam open, so the adversary can have access to his video footage. The adversary then uses our scheme, which uses the small movements from the arms and upper arms and shoulders to predict what the user typed. Our framework is split into three phases: a pre-processing phase, a keystroke detection phase, and a word prediction phase. Due to time constraint, we will only cover the overview. Please read the paper for more details. In the pre-processing phase, our objective is to remove the background and segment left and right arms. To do that, we take a frame for any background and we remove the background and then we segment the arms. Again, more details in the paper. The keystroke detection phase, we want to find the frames which contains where the button was pressed, the key presses happen. To do that, we will process both the left and the right arms frames separately, which we obtain from the pre-processing phase. For each arm, we apply our own keystroke detection algorithm, which utilizes the changes of structure similarity index measure, SSIM, between different consecutive events. SSIM measures the structural symmetry between two images. The lower the value of SSIM, the more changes occur in an image. We found that typing occurs when there is a relative max peak followed by a relative min peak within certain statistical thresholds. However, it's important to note that these peaks and pattern is not only for key presses, it's also for mouse presses, for finger tapping, and other potential activities. So, we want to differentiate between key presses and non-key presses. So we propose 4 heuristics. The first one is the max speeds filter. The max speed filter filters out potential keystrokes that are consecutive but above expected typing speed. A location filter filters out the potential keystroke where the user hands appears to be much further from the keyboard, for example when using a mouse. A min speed filter filters out potential keystrokes that are isolated or in below expected typing speed. An exclusive filter filters out keystrokes that are exclusively used in one hand, such as mouse clicks. So, our final phrase is word prediction. We want to use the frames from the keystroke detection to find what words was typed. Our first sub-process is to segment the shoulder. We would take the outer edges of the shoulders and arm, then uses the fact that the shoulders are wider than its height, we determine that any 2 points in the shoulder should not have an angle greater than 45 degrees. So we take the first shoulder pixel and compute the angle for all the other pixels until we find one pixel where all the other pixels after it is greater than 45. This would be the split between the upper half, which is the shoulder, and then the lower part, which is the arm. Now this separation is important as the joints in our body causes the movement, while there are many joints in the shoulders. Between our elbow and the shoulder exist no joints, meaning that section of the arm moves uniformly. We then apply optical flow between two consecutive potential keystroke frames in the same arm to see the movements. Using the average optical flow result on both the shoulder and the arms, we calculate an inter-keystroke direction. Those inter-keystroke direction are nothing more but an estimation of the relationship between the two keys that press. Because we do not know the user finger size nor the position of the keys, we will assume that a user finger could be at any of the edges of a button. So let's take an example. If we want to go D to A, we know that the movement is a west movement, but also the movement could be from the lower edge of the D to an upper edge of A, which exhibit a north movement, or an upper edge of the D to a lower edge of an A, which exhibit a southern movement. So D to A is both northwest and southwest at the same time. Likewise, D to itself can be northeast, northwest, southeast, and southwest, as it could be in any of the edges, to any of the other edges. After we find a profile for all the possible inter-keystroke directions, we would try to match it with a dictionary. The dictionary would be ranked, and the dictionary would have all the profiles. The adversary must create this dictionary beforehand with its own respective direction profiles. Our output would be determined by the rank. The first match would be the highest ranked output, and then the second one would be the second guess. Let's take an example. Assume a user typed cat. Cat could produce two directions, northwest and northeast. We try to match it in the dictionary and see which of the words have the same profile. Cat and sat, both of them have the same profile. Sat, S2 and A is also a northwest direction. As a result, both of them could be a possible output. Depending on their rank, they would be outputted. On the other hand, 8 have an A to T for the first two keystrokes, which means a northeast movement. Since the northeast movement does not match the first northwest movement, it means that 8 is not a possible result, so it will be omitted. Now we experiment our experiment under two different settings, the in-lab and the at-home. In the in-lab, we wanted to evaluate how different parameters take consideration to our framework, such as different mouses, different keyboards, and etc. At the at-home, we wanted to see how practical is our framework in the real-world scenarios. For the in-lab, all the experiments was done in one office room inside a university. They were given the equipment, the keyboard, the mouse, the webcam, and etc. They were asked to type 300 English words, which we gave to them, so they were dictionary bounded, and only typing activities was done. In the at-home, the participant chose their own location, and we did not tell them where to go. The participant chose their own equipments, laptops, keyboard, and etc. And the participants not only had to type English words, but also passwords and websites to reflect a more realistic setting where passwords and websites could be typed. Because we asked the users to bring their own words, passwords, and websites, the dictionary we had as an adversary does not contain all the text that the user typed. Finally, we asked the participants to have non-typing activities in the middle, somewhere at their time of discretion. These typings include watching a video, playing a game, and reading an article. So the in-lab, again, just to recap, it's a controlled setting, while the at-home is a more realistic setting. We evaluate our keystroke detection algorithm under different statistical thresholds. Parameters. We selected the following parameters, which would lead us to the most balanced option between the recalls and precision, with a 93% in precision and a 92% in recall for detecting keystroke events. In the in-lab, we now see the text recovery. In our experiment, we utilized the concept of top X prediction, which means that a text is predicted in the top X prediction. We utilized 3 different webcams in our lab experiment. Logitech, it's a 1080p normal webcam, an NVIDIA 1080p normal webcam, and a Lenovo, a laptop webcam 720p. So, we saw overall that the laptop webcam performed the worst due to both close positioning of the webcam and the lower resolution. On average, it predicted 44% of the words within the top 200, while the Logitech predicted 75% of the typed word and the NVIDIA 70% of the typed word. Now we look at the different typing styles. Hunt and peck was the most vulnerable to our attack, with an 83% of the words prediction in the top 200, while the hybrid had 74% and the touch typer had the 71%. The main reason behind this is that the hunt and peck typers moved the most, which was easier for our framework to predict, while the touch typers rarely moved their hand location, only fingers, which had very minor movements impact on the shoulders. We now compare the two aspects. First, the video between the audio, and we saw on average both of them had around 65%. However, we also saw that the audio percentage with a slight amount of noise could deplete its recovery rate to even around 7%. So, our at-home experiment, the keystroke detection, had a lower 13% in both recall and precision compared to the one we found in the in-lab. The reason behind this is because we had the non-typing activities. Some of them was not that accurate in filtering out, and we had more false positives. At the at-home evaluation, now we did not just recover English words, but also passwords and websites. On average, 66% of the website type was able to be predicted in the top 50, while only 19% of the password was recovered in the top 50 and 21% of the words recovered in the top 50. So the word recovering is lower than the in-lab, but one thing to notice is 75% of the typed passwords was not in our dictionary, and 25% of the typed English word was not in our reference dictionary. This led us to go to some of the limitation, and one of the main limitation is a reference dictionary. We require a ranked reference dictionary, and the creation of such could be a hard task. But since our scheme is about the relationship between the keystroke rather than predicting the keystroke itself, a reference dictionary is required. Also, significant changes in lightning may impact our accuracy because we use an optical flow which assumes that the lightning of the image should not be changed. A key takeaway message here is we created a new keystroke inference attack that uses the video feed of an online video call, and we were able to test how that it is feasible to predict what a person typed using the video feed. One other thing to notice is that in the real world setting, this could be challenging. For the main reason is that the reference dictionary that is required is something that is a challenge for an adversary to create. Thank you for listening, and I'm happy to take any questions.